Good morning, guys. Now we'll start our next lecture, next topic, numerical treatment to one-dimensional bar element. Okay, so in previous lecture, actually we have discussed some problems related to your spring elements. Okay, we have solved some problems related to your spring systems, which includes 2, 3, 4 nodes. Okay, so as we have converted these elemental stiffness matrices to global stiffness matrices, then we have applied our elimination approach to get your displacement values as well as finally your force values or reaction values. Okay, now we will start our next session regarding your numerical treatment to one-dimensional bar element. Okay, so as we know that in first lecture, actually we have derived this elemental stiffness matrix for bar element. As we know that the elemental stiffness matrix for spring element is given by this square matrix as E is equal to K minus K. Okay, so similar to that, we can write our elemental stiffness matrix for bar element. Actually, we have derived this elemental stiffness matrix in our previous lectures. Okay, so and this elemental stiffness matrix for bar element is given in terms of E is equal to, in bracket, AE by L minus AE by L plus minus AE by L and finally plus AE by L. Okay, so this is your elemental stiffness matrix for bar element. Okay, and actually we have written this elemental stiffness matrix in short form as E is equal to, we have taken AE by L as common, AE by L into the square matrix, which includes 1 minus 1 minus 1 1. Okay, or you can write the elemental stiffness matrix similar to this elemental stiffness matrix for spring element, but instead of K you need to write down this AE by L. Then you will get the elemental stiffness matrix for bar element. Okay, so this is for your spring element, where the value of K, or K means spring constant, or stiffness, the stiffness value is given for the spring system. Okay, so for example, K is equal to 200 Newton per meter. Okay, so in this way you will get this elemental stiffness matrix for the spring system. But for rod element or bar element, you need to find out this K is equal to A by L, where A is the area of that bar element, E is the Young's modulus of that bar element, and L is the length of that bar element. Okay, so this is the way to find out the stiffness value for this elemental stiffness matrix for rod element or bar element. Okay, so actually we derived this equation in our previous lectures. Okay, so by using this elemental stiffness matrix, procedure is same to find out the stresses or reactions or displacements in the rod element. The procedure is same. So procedure is what? First you need to find out the elemental stiffness matrix for the bar element or rod element. Next is what? Assemble the elemental stiffness matrices globally, means you need to construct the global stiffness matrix. Okay, this is the second step. Third step is what? Apply the boundary conditions, means as we have applied the boundary conditions in our spring system, similar way we will apply the boundary conditions to your bar system. Okay, means apply the boundary conditions for force vector as well as apply the boundary conditions for displacement vector. Then next is what? Apply the elimination approach to get the displacement values first. Okay, by applying the elimination approach, you will get the eliminated equations only. Okay, means you will get the 2 or 3 equations. By using this or by solving these 2 or 3 equations, you will get the displacement values first. Okay, so you will get the displacement values, for example U2 and U2. These are the unknown displacements. You will get first these values by applying such procedure. Then next is what? Then by using these displacement values and by using the force equations, you will get the reactions or forces. Okay, means you will get the support reactions. For example, R1 and R2 if the 4 node system is there. Okay. So first you will get the displacement system, then you will get the reactions or forces at the supports. Then next is what? By using this, you will get stresses. Sigma 1, sigma 2, sigma 3 for example. So the formula to find out the stress is what? Stress is given by the formula for if there are 3 elements, 3 rod elements. Suppose there are 3 rod elements, first end and the last end or last one is flexible. Then the elemental stresses in this element 1 is given by this formula. Actually we have derived this equation also in our previous lecture. So sigma 1 is given by, this is related to your first element. So it will become E1 by L1 in bracket U2 minus U1. This is your U2, this is your U1. So formula to find out the stress in element 1 is given by E1 by L1 into U2 minus U1. Similarly, sigma 2 can be written as, instead of E1 by L1, you need to write down E2 by L, because here we are determining the stresses in element, so it will become E2 by L into the displacement difference between the two displacements, U3 minus U2. So it will become U3 minus U. And finally, sigma 3 is given by the formula E3 by L3 in bracket difference between the two displacements for this element. This is nothing but your U4 and this is nothing but your U3. So it will become U4 minus U sigma. Okay. So as you have solved such type of examples in your strength of material, as you have gone through this in your strength of material theory, but by applying our finite element procedure, we will check or we will cross check the answers by using this procedure. Okay. Now we will solve some examples related to your one-dimensional bar element or one-dimensional rod element. Okay. So procedure is same, means first you need to find out the elemental stiffness matrices by using this formula. E is equal to A by L minus A by L minus A by L, A by L. Means you can write this as also by taking A by L common, this will become A by L in bracket 1 minus 1 minus 1 1. So this is the formula to find out the elemental stiffness matrices. The next step is what? Next step is what? So by using these elemental stiffness matrices, assemble these elemental stiffness matrices globally. Means construct the global stiffness matrices, assemble these elemental stiffness matrices globally. So next step is what? The construction of global stiffness matrix. Next step is what? Then third step is what? Apply the boundary conditions. Apply the boundary conditions means apply the boundary conditions for force vector as well as for displacement vector. The next step is what? Apply the elimination approach to get the displacement values first. So by applying the elimination approach, you will get 2 or 3 equations. The remaining 2 or 3 equations you will get. By using these equations, you will get the displacement values. And finally, by using the displacement values, you will get the forces or reactions. And by using these displacement values also, you will get the stress values, sigma 1, sigma 2 and sigma 3. Okay. So in this way, you can proceed to find out or to get the values of stresses in each element. Okay. Now we will see some examples. On the first example, related to your FEA application to one-dimensional bar. Okay. So let us see one example. And actually such type of problems, these problems are asked for 8 to 10 marks in your INSEM as well as in your ENSEM examination. So we will see an example related to your one-dimensional bar system. Okay, so this is the example. One second. This is the 2-bar system, but there you are some force at this node which is equal to 30 kilonewton. Its total length is equal to 300 mm, and its total length is also equal to 300 mm. This node is at length 150 mm, and they have given the nodes as 1, 2, 3 and 4. Then this is the aluminum component. This material is made of aluminum material which has area equal to 250 mm square, and this is made up of cast iron which has area equal to 400 mm square, and the value of E, Young's modulus, for both elements or material is given equal to 200 gigapascal. Okay, so this is the example, and the question is what? First, find out the displacements at node 2 and node 3, means U2 and U3. Second question is what? Find out the reactions at support, means at node 1 and at node 4. So R1 and R. And third question is what? Find out the elemental stresses in each element. So as there are 4 nodes, means there should be 3 elements. This is considered to be a first element, this is considered to be a second element, this is considered to be a third element. Okay, as they have denoted the elemental nodes in this system. This is first, second. So between first and second, this is your first element. Between node second and third, this is your second element. And between node 3 and 4, this is your third element. So there are 3 elements. So they have asked to find out the elemental stresses in each element. So as there are 3 elements, 1, 2, 3. So you need to find out 3 stresses: sigma 1, sigma 2 and sigma. Okay. Actually, this example is asked in your end semester examination for 10 marks. Okay, in last year. So now we'll try to solve this example. So now, first is what? First step is what? First, find out the elemental stiffness matrices. Okay, as shown in the system, as there are 4 nodes, it means our global stiffness matrix, order of global stiffness matrix should be equal to 4 by 4. Then next is what? As first node and last node is fixed one, so at these nodes we need to find out our reaction lines. Next, at second node, the force value is given in positive horizontal direction. So this is given equal to 30 kilonewton, means at node 2 force value is known. At node 3 the force is not given, so it should be equal to 0, or it should be assumed to be 0. Then next is what? Now we will go step by step. So first step is what? Find out the elemental stiffness matrices. Okay. So E is equal to 200 gigapascal. E is equal to 200 gigapascal. Okay. Now, so first is find out the elemental stiffness matrices. For example, now elemental stiffness matrices we will denote it by K1. K1 is equal to, as we know that the standard formula to find out the elemental stiffness matrices for rod element as A by L in bracket 1 minus 1 minus 1. So this is your standard elemental stiffness matrix. Elemental stiffness matrix for rod element. Now, by using this elemental stiffness matrix for rod element, we will find out the elemental stiffness matrices for this given system. So this will become K1 is equal to A by L. Actually, this is applying here we are applying this for first element. So it will become A1 T1 by L1 in bracket 1 minus 1 minus 1. Okay, so K1 will become, now A1 is what? A1 is given. A is, for this element, A is given equal to 250 mm square into E1. E1 is what? 200 gigapascal. Now, here we will get the displacements in mm. So we need to convert all the dimensions in mm. Okay, here already area is in mm square. So we need to convert this E1 in also Newton per mm square. Actually gigapascal. So we need to convert this into Newton per meter square. So 200 into gigapascal is 10 raised to power 9 pascals. So E will become 200 into 10 raised to power 9 pascal is Newton per meter square. So E will become 200 into 10 raised to power 9 into Newton per 1 meter square is equal to 10 raised to power 6 mm square. Okay, 1 meter square is equal to 10 raised to power 6 mm square. So E will become 200 into 10 raised to power 3 Newton per mm square. So finally, you need to write down E is equal to 200 gigapascal, which is nothing but 200 into 10 raised to power 3 Newton per mm square. Actually, we know that 1 megapascal is equal to 1 Newton per mm square. Actually, we know this relation here from your strength of material theory. 1 megapascal is equal to 1 Newton per mm square. So, 200 gigapascal, we can write 200 gigapascal is equal to 200 into 10 raised to power 3 megapascal. Okay, so it will become 200 into 10 raised to power 3 Newton per mm square. From this relation, this will become 200 into 10 raised to power 3. 1 megapascal is nothing but 1 Newton per mm square. So 1 Newton per mm square. So this will become 200 into 10 raised to power 3 Newton per mm square. As all the dimensions are in mm and our expectation of displacement is in mm, so we need to convert this gigapascal into Newton per mm square. So 1 gigapascal is equal to 10 raised to power 3 Newton per mm square. So 200 gigapascal is equal to 200 into 10 raised to power 3 Newton per mm square. So instead of this, we will write here 1, as we know that 1 gigapascal is equal to 10 raised to power 3 Newton per mm square. So 200 gigapascal, it will become 200 into 10 raised to power 3 Newton per mm square. Okay, so just write down this value of the Lenz's modulus into this equation. So A1 is equal to 250 into E1 is equal to 200 into 10 raised to power 3 divided by L1. L1 is for this element only. So L1 will become 150 into 1 minus 1 minus 1. Okay, so by simplifying this, you will get 0, it will cancel 5, 3, 15, 5, 5, 25. So 20, 15 to 20 divided by 3. So this will become here, this will become 50 into 20 into 10 raised to power divided by in bracket 1 minus 1 minus 1 1. So finally this will become K1 is equal to, this is 1000 into 10 raised to power 3 divided by 3. Okay, now which is nothing but equal to 10 raised to power 10 into 10 raised to power 5 divided by 3. So this will become 3.33 into 10 raised to power 5. These two will get here 5, 10 raised to power 5 into 10 into 10 divided by 3. 10 by 3 is equal to 3.33 into 10 raised to power 5. So finally we will get here 3.33 into 10 raised to power 5. Okay, so we will multiply, take 3.33 into this matrix. So finally you will get K1 is equal to 10 raised to power 5 in bracket 3.33 minus 3.33 minus 3.33 3.33. Okay, so in this way you will get first elemental stiffness matrix K1 as 10 raised to power 5 3.33 minus 3.33 minus 3.33 3.33. Then next is what? This is for first element. Now we will apply our same formula to second element. Means to find out the second elemental stiffness matrix. Now here you will see that now K2 is equal to what? A2 E2 divided by L2 in bracket 1 minus 1 minus 1 1. Okay, so this will become equal to A2 means what? Area for this material is U1 and this material is a part of this element is part of this material. So A2 is what? A2 is equal to 250 mm square. 250 into E2 is what? E is also common for this all materials. So E is equal to nothing but 200 gigapascal. 200 gigapascal is nothing but 200 into 10 raised to power 3 Newton per mm square. 200 into 10 raised to power 3 divided by L2 is what? L2, this is the L2. L2 is what? 150 mm because total is 300 mm. First, for first element it was 150 mm, then for second element it should be equal to 150 mm. So it will become equal to 150 into 1 minus 1 minus 1 plus 1. Okay. So this is the same value as we have calculated for element 1. So it is nothing but this value, this matrix value, it is for element 1 as well as for element 2 because all the values are same here. Your area is same, E is same, as well as your length is same. So all the parameters are same for this element 2. So as we have already calculated, determined our elemental stiffness matrix for element 1, as the parameters for elements 2 are same as compared to first. So you will get K2 also equal to 10 raised to power 5 in bracket 3.33 minus 3.33 minus 3.33 plus 3.33. So this K1 is equal to K2 is equal to this matrix. Okay. So here you got K1 is equal to K2 is equal to 10 raised to power 5 in bracket 3.33 minus 3.33 minus 3.33 and 3.33. So okay, so K1 K2 is equal to 10 raised to power 5 3.33 minus 3.33 minus 3.33 3.33. And next is what? Find out the third element stiffness matrix. So K3 will become A3 into E3 divided by L3 in bracket 1 minus 1 minus 1. So this will become A3. A3 means this area. This is nothing but 400 400 into E3. E3 means same. 200 into 10 raised to power 3 divided by L3. L3 is nothing but equal to 300 mm. So it will become 1. This will get 800 into 10 raised to power 3 divided by 3. So it will become 8 by 3 into 10 raised to power 5. So finally, this will be 8 by 3 is nothing but 2.66. Okay, so this will become 2.66 into 10 raised to power 5 in bracket 1 minus 1 minus 1. Okay, so in this way you will get the elemental stiffness matrix for this third element. So you can write this elemental stiffness matrix as K3 is equal to 10 raised to power 5 in bracket 2.66 minus 2.66 minus 2.66 and 2.66. Okay, so in this way you will get elemental stiffness matrices for element 1, 2 and 3. As for element 1 and 2, all the parameters are same, so elemental stiffness matrix is same. Then for third element, this is the elemental stiffness matrix. Now next step is what? Next step is what? Assemble these elemental stiffness matrices globally to get the global stiffness matrix. So our global stiffness matrix, order of global stiffness matrix. What is the order of global stiffness matrix here? As there are 4 nodes, 1, 2, 3, 4. So the order of that global stiffness matrix will become equal to 4 by 4. Okay, as there are 4 nodes means number of nodes is the order of that global stiffness matrix. So as there are 4 number of nodes, so the order of global stiffness matrix will become equal to 4 by 4. So K, finally this K will become equal to 1, 2, 3, 4. So finally this K will become equal to 1, 2, 3. Okay, so as we know that from elemental stiffness matrices 1, 2 and 3, 10 raised to power 5 is common. Okay, so 10 raised to power 5 is common. So take this 10 raised to power 5 as a common into. Okay, now write down the elemental stiffness matrix, first elemental stiffness matrix globally. So as we know that the position of the elemental stiffness matrix is it between node 1 and node 2. So we need to write down this matrix between position 1 and 2. So as we know that, as we have previously written the elemental stiffness matrices globally. So in this here also we will write down this elemental stiffness matrix globally as 3.33 minus 3.33 minus 3.33 3.30. Okay. The next is what? Second elemental stiffness matrix. As we know that the value for the second elemental stiffness matrix is the same as for 1. So we need to write down this elemental stiffness matrix globally between position 2 and 3. Here as for our first element, position is what? Between 1 and 2. But for second element, position is what? Between node 2 and node 3. So we need to write down this elemental stiffness matrix between position 2 and 3. So between 2 and 2 and, so this will become, here it will become plus 3.33 minus 3.33. This will become minus 3.33 plus 3.33. Next is what? Write down this third elemental stiffness matrix global. So write down this in between position 3 and 4. So it will become between 3 and 4. This is the box. So 3 and 4. So plus 2.66 minus 2.66 minus 2.66 and 2.66. Okay. So in this way you can write your global stiffness matrix. Okay, so as the remaining elements will become equal to 0, 0, 0, 0, 0. Okay, so this is the global stiffness matrix, and this can be written by using your elemental stiffness matrices. Okay, now next step is what? Next step is what? So next, first simplify these elements. 3.33 plus 3.33, it will become 6.66. This will become 3 plus 2, 5.99. This will become equal to 5.90. Okay, so by simplification you will get 10 raised to power 5 into 3.33 minus 3.33, 0, 0. In this way you can write your global stiffness matrix. Now next step is what? Write down the force and displacement relationships. As we know that the force and displacement relationship is given by this equation. F is equal to global matrix times displacement vector. So in this way you can write your global stiffness matrix now. So you can write, as we know that for this first node F1 should be there, here F2, U2 should be there, here F3, U3 should be there, here F4 and U4 should be there. These are the nodal forces and nodal displacement. So in this way you can write. In similar way as we have applied this step for your spring system, we can apply the same step for this bar system. So it will become F1, F2, F3 and F. Okay. So is equal to now is equal to into U1, U2, U3 and U4. Yes. So in previously actually we have applied this step to our spring system also. Same step here we are going to apply. So by writing this global stiffness matrix into force and displacement relationship. So in this way you will get here 4 force equations. F1, F2, F3 and F4. Now next step is what? Apply the boundary condition. Now apply the boundary condition. Means first apply the boundary conditions for displacements and then for forces. So for displacements, as we know that node 1 and node 4 is fixed one. If the nodes are fixed one, then displacement should be 0. So here U1 will become 0 and U4 will become 0. And for U2 and U3, these nodes are free, means there will be some displacements will occur there. So U2 and U3, these are the unknowns. So U1 and U4 will become 0. U1 and U4 become 0. U3 is unknown. U2 is unknown. U3 is unknown. Then next is what? Apply the boundary conditions for forces. So as we know that this one is fixed one, this is also fixed one. So here we will get reactions. So F1 is equal to R1, F4 is equal to R4, and F2, as F2 is given one, 30 kilonewton, means the value for F2 is given as 30,000, and F3, the value of F3 is not given, so it will be equal to 0. So finally, your force vector will become equal to this R1 for second node, 30,000, third node 0, fourth node R2. Okay. In this way, this is your first equation. Second, 1 minute. This is your R1, 30,000. Finally, this is what? So in this way, you can write here as this is 0, U2, U3 and In this way, you can write. In this way, you can write the equations. Okay. Now, next step is what? Apply the elimination approach. Okay. So, first find out where the displacement value is 0. This step is what? First find out the where, in which equation your displacement value is 0. So as we know that from right RHS, we come to know that your U1 is equal to 0 and U4 is equal to 0. This is nothing but your U1 and this is nothing but your U4. So from this we come to know U1 is equal to 0 and U4 is equal to 0. So from this we will eliminate U1 row as well as U1 column. Means first row and first column. We need to eliminate first row and first column as U1 is equal to 0. We need to eliminate first row and first column. First row and first column. Then next, where is the displacement is 0 in RHS? Here U4 is equal to 0. So we need to eliminate fourth row as well as fourth column. So we need to eliminate fourth row as well as fourth column. Okay, so in this way, this is your fourth column. So in this way you have eliminated first row, first column, fourth row, fourth column. Now next is what? Write down the remaining equations to get the displacement value. So write down the remaining equations here. So we will write here the remaining equations as, from this, by after elimination we will get the remaining values. These are the remaining values. Okay, these are the remaining values. So here also these are the remaining values. Okay, so from this you can write 30,000 is equal to 10 raised to power 5 into this matrix. 10 raised to power 5 into this matrix is nothing but 6.66 minus 3.33 minus 3.33 and 5.9. Okay, this is your matrix value, 10 raised to power. Don't remember to take this value into account because in your exams you just forward this to take into account, 10 raised to power 5. And by forwarding these values, you will get wrong answers. So 10 raised to power 5 we need to take into account while solving these examples. So 10 raised to power 5 into this matrix into U. Okay. So this is nothing but your two equations. It means 30,000 is equal to 10 raised to power 5 in bracket 6.66 into U2 minus 6.66 into U2 minus 3.33 into U. This is your first equation. And second equation is what? 0 into 10 raised to power 5 minus 3.33 into U2 plus 5.99 into U. So this is your, these are your two equations. Now by using these two equations, you will get U2 and U3. So just simplify these two equations. Means by simplifying 30,000 divided by 10 raised to power 5. So 30,000 divided by this 10 raised to power 5 is equal to 6.66 times U2 minus 3.33 times U. 0 divided by 10 raised to power 5 means 0 divided by 10 raised to power 5. It is nothing equal to 0 actually. It is equal to minus 3.33 times U2 plus 5.99 times U2. So by simplifying this, you will get 10 raised to power 5. 10 raised to power 5 is 1, 2, 3, 4, 5 is 0.3. 0.3 is equal to 6.66 times u2 minus 3.33 times u3. And then next 0 by 10 raised to power 5 is 0 is equal to, because 0 by 10 is equal to 0, minus 3.33 times u2 plus 5.99 u2. So in this way, here now you will get two equations, and by solving these two equations in calculus, you will get u2 is equal to and u3 is equal to. So by solving these two equations, you will get u2 as the value of u2 is equal to 0.0623 mm, because you will get the values in mm only, because we have converted all the units into mm, and u3 is equal to 0.03461 mm. So in this way, you will get these two values. u2 is equal to 0.0623 mm and u3 is equal to 0.03461 mm. Now next is what? This is your first question. The second question was find out the reactions. So to find out the reactions, by using this first equation and by using this fourth equations, you will get the reactions that supports one and at left support as well as at right side. So use this equation R1. So R1 is equal to 3.33 times 0, it means 0, minus 3.33 times u. Okay, so minus 3.33 times u. 0 times this, 0 times this. So this is nothing but equal to minus 3.33 into u2 is nothing but 0. Here, just here. So remember that you need to take this 10 raised to power 5, because 10 raised to power 5 into this matrix. So that's why you need to take here 10 raised to power 5. You need to take this value 10 raised to power 5. Just don't forget this. Take it in this account, this value. 10 raised to power 5 into this value is equal to 10 raised to power 5 into minus 3.33 into u2 is what? 0.0623. Okay, so from this you will get R1 as, from this you will get R1 as, by simplifying this you will get R1 as R1 equal to minus 2770 Newton. 20,770 newtons is the value for your R1. Similarly, you can find out R2. So R2 is what? R2. For R2, sorry, R4. From this equation, you will get R4. So R4 is equal to 0 times U1 means 0. 0 times U2 means 0. Minus 2.66 times U2. Here, you need to take into account this value 10 raised to power 5. So 10 raised to power 5 into minus 2.66 into U3 plus 2.66 into 0 is 0. So from this, you will get R4 by putting the value of U3 is equal to 0.03461, you will get R4 as, so R4 equal to, R4 will become minus 923 minus 9230 newtons. 9230 newtons. You will get this minus 930. In this way you will get R4. So now whether this R1 and R4 is correct, So whether these values u2 and u3 are correct, you need to cross check these values with your this force 30 kN. This 30,000 newtons must be balanced by these two reactions. Means reactions at left support and reactions at right support. So to balance this 30,000 newtons, actually this is applying in this right direction. So this R1 and R4 must act in left direction. So negative sign it means these are in compressive direction, and just we need to add this and we need to cross find. So 0, 7, 3, 0, 1, 10, 1, 0, 1. It means this force is balanced by these two reactions. Okay, this force is acting in positive right direction. So to balance these 30,000 kN, we need to apply these two reactions in left direction or in compressive direction. Then and then only this will be balanced. So your answer is correct because this is balanced. This force is balanced by this R1 and R4. It means your U2 and U3 values are correct. Okay. This is the small technique to cross check the values. Okay. Now next is what? To find out. These are the reactions. Now find out the stresses in the element. Okay. Now we will find out the stresses in the element. We will find out the stresses in element now. Okay. As we know that stress value sigma 1 is equal to what? E1 by L1 in bracket U2 minus U1. This is nothing but stress in element 1. Stress in element 1. It is nothing but E1 by L1 into difference between the displacements for that element. Means displacements U2 minus U1. U2 minus U1. So in this way, you will get sigma 1 as E is what? 200 into 10 raised to power 3 divided by 10 raised to power 3 because we are taking in Newton per mm square. So 200 into 10 raised to power 3 divided by L1 is what? 150 mm. 150 mm into U2 is what? 0.062 minus U1 is what? Actually U1 is equal to 0. It is equal to 0. So this will become sigma 1, it will become equal to sigma 1 will become 83.08 Newton per mm. Similarly, sigma 2. So what will be the formula for sigma 2? This is nothing but E2 by L2 in bracket difference between these two displacements. U3 minus U3 minus. So sigma 2 will become E2 is same 200 into 10 raised to power 3 divided by L2 is also same. L2 is what? 150. Now U3 is what? 0.034 61 minus 0.0623. So you will get sigma 2 as sigma 2 it is equal to 36.92 Newton per mm square. And similarly sigma 3 the formula is E3 by L3 in bracket difference between these two nodes, two displacements U4 minus U3. So it will become 200 into 10 raised to power 3 divided by L3 is different now. L3 is equal to 300. L3 is equal to 300 into U4 is what? U4 is equal to 0 because of this fixed force. So 0 minus U3 is 0.03461. So sigma 3 is equal to 23.08 Newton per Actually, these two values should be negative. This should be compressed. It should be negative because 0.034 minus 0.062. This value it should be negative. Similarly, 0 minus 0.03 it should be negative. So sigma 2 and sigma 3 should be compressed and sigma 1 should be tensile. Okay. So in this way you will get sigma 1, sigma 2 and sigma 3. Okay. So in this way we have determined your stress values, displacements as well as your reactions. So such type of problems will be asked in your end-sem examinations for 10 to 12 marks. If such type of problems are asked for 12 marks, then 4 marks up to these displacement values. 4 marks is for your reactions and 4 marks is for your stresses. Actually, up to these displacements, step by step you will get 6 marks. Then 2 marks should be for stresses and 2 marks should be for your reactions. Okay, so in this way you will get this example for 10 to 12 marks. In INSEM, if such type of examples are asked in INSEM, they will ask to find out the values of your displacement. Okay, this is for your 6 or 8 marks. So this is the procedure. So first one is what? First you need to eliminate. You need to find out this elementary stiffness matrices, as there are 3 elements, 1, 2, 3. So you need to find out 3 elementary stiffness matrices. Then second is what? You need to construct the global stiffness matrices by using these elementary stiffness matrices. Then third step is what? Write down these global stiffness matrices into your force and displacement relationships. Then next is what? Apply the boundary conditions for forces as well as for displacements. Then next is what? Eliminate. By applying the boundary conditions, eliminate this global stiffness matrix by using your displacement values. So after eliminating, you will get the remaining equations. By using these 2 equations or 3 equations, you will get first displacements, then you will get the reactions values, and then finally you will get the stress values. Okay. So in this way, you can proceed to find out the displacement, reactions as well as stresses. So same such type of problems will be asked in your exam. Okay. So in this way, we have determined the displacement, forces and stresses. So in next lecture, we will solve some such type of examples of, as we have solved this for 2 elements, we will proceed for, here we have actually solved for 3 elements, we will proceed for 4 elements, means your global stiffness matrix will become of order 5 by 1. In your next lectures, we will solve such type of examples. Okay. So here we will conclude our lecture. Okay, thank you.